Yesterday we studied the sandwich theorem, right? Suppose we need to compute the limit of x squared times x sine of 1 over x when x approaches 0. We see that when x approaches 0, 1 over x here is undefined. Okay? So we cannot substitute it directly here. That is why we bound it by two functions. The first one is negative x squared, and the second one is x squared. And as x approaches 0, both these two functions goes to 0. Therefore, the limit of the inside function should also goes to 0. That is the squeeze theorem, right? Here is a recommended too. At home, you can plot it, this function on decimals, to see how it behaves. It's a very useful tool. Okay, you see that here. The red curve is the x squared curve, and the blue one is negative x squared. And this x squared sine function here, it is between these two. When you zoom it in, you see that they bounce this sine function here, right? One more thing. Yesterday we just reviewed a lot of things about trigonometry. It's not directly related to the section 2.3, but throughout the semester you will need to face trigonometries a lot. And in the future, how to and any other course you need to deal with that. That is why I spend a lot of time reviewing these. Try to go home and play with a unit circle. Understand it, you will never forget it. That is one thing. And today, we will study the section 2.5. Okay? Now, take 2 minutes to quickly scan the notes I gave you. Sorry, if you haven't got one, you can go to Moodle and download it, print it out. Sorry, I print a lot. I don't know. What are we studying today? Nearly, right? So, the definition, a function is continuous, or sometimes it is satisfying three conditions. Okay? The first slide. So if at this point A is a given number, right? We say that this function is continuous at A if its f at A is defined. The first thing. The second thing, the limit when x approaches A exists. It means that the left hand limit and the right hand limit will be the same. Thank you. Good job. And the limit when x approaches A of fx here will be exactly the evaluation of the function at the point A. Okay? In other words, a function, you can imagine this. A continuous function means that when you draw, you don't have to, it will be, in order to draw it, it will be a continuous line. You don't have. So just definition, reread it. And if it's not continuous at A, we say it is discontinuous at A, or it is not continuous at A. Okay, some names. Now let us play with this example. Fill in the blank. First, the figure 2 here shows the graph of a function at which numbers is f continuous and y continuous. So now look at this graph. So if x is the value in the x direction here, if it is smaller than 1, is it continuous? Yes, right? And then at x is equal to 1, is it continuous? Good job. It's not continuous here, because when we draw this point, then we need to start as a hole right here, right? Then, so what should we fill in the blank here? It's undefined, right? Thank you. How do we know it's undefined? Yes, the whole. Good job. So then it is continuous from 1 to 3. What is the value of this function at s f is equal to 3? It's somewhere here, right? A negative number. Let us call it -1, for example, right? Then it should be -1. We project from this point, the horizontal line here will tell us the value of this. Okay, good job. And it is defined, right? But what is the limit of the function fx when x approaches 3? Why do you know that? Louder, please. You're right. And what is the value when x approaches 3 from the left? Let's say this is -1, okay? Then it should be this value, right? And if this point right here is, say, it is 2, then limit of f of x when x approaches 3 from the right-hand side, what is it? 2. And the right-hand limit and the left-hand limit are different. So the limit of this does not exist, right? Are different. Good job. Are you okay? Very good. The next part. Can you help me? So at A is equal to 5. F at 5 is this point, right? The solid point right here is defined. However, the limit of this, what is the limit of this when x approaches 5? Yeah, very good. Let us guess it is 1. Very good. It exists, right? The left-hand limit and right-hand limits are the same, but the limit when x approaches 5, how is it compared to f at 5? Different, right? So this example shows the conditions of the continuous here. Each of the case violate one of the term in definition. So it is not continuous at 3 and 5 and 1. Okay? Is the definition of continuous function clear now? Good job. People on Zoom, is it clear? Okay, good. Let us continue. Now, suppose you're given 3 questions, A, B, and C. Question A. Notice f at 2 is, so f is discontinuous at 2. Undefined, right? Why it is undefined at 2? Yeah, this is a rational function, right? At x is equal to 2, it will be something divided by 0. This function is undefined at 2. Therefore, it is discontinuous at 2. Okay? Question B. F at 0 is equal to 1. Why do we know that? It's given here, right? In the definition of a branch function. So we know this. It is defined. How about this? The limit of this guy, what is it? It's undefined at 0, right? Very good. On limit, then let us say does not exist. Okay? Why? Sorry? Good question. Why it does not exist, right? So can you help me with this? Why the limit when x approaches 0 of 1 over x squared does not exist? Because when x comes closer and closer to 0, the denominator will be also coming closer and closer to 0, right? 1 is a given number divided by a very small number. Do you remember this? Okay, let us play with this. So the function 1 over x squared okay, do you see the graph of this? When x comes closer and closer to 0, the function value will be very big. It goes to infinity. We've done this before, okay? Or you can use your calculator. Suppose if x is 0.1, then what is f of x? 100, right? Okay. How about when x is 0.01? Will be 10,000. If x is smaller, 10 to the minus 3 square, 10 to the 6, 1 million. Okay, very big later. So in other words, we know that the limit of this function goes to infinity, or we say it does not exist. It does not converge to a specific number. Okay. Sorry. Yes, it goes to infinity, or it is equal to say that it does not exist. Because it exists when it converges to a specific number. For example, 2, 1, 3, or 1,000, whatever, but it should be a specific number. But here, it doesn't, right? So it violates which definition, which items? The second one, right? Okay. Therefore, it is discontinuous at 0. Is the second example here? If not, just raise your hand. Okay. How about the third one? They say that, okay, f at 2 is equal to 1. We know this because it is given right here, the branch function. And the limit of this guy, how can we compute it? Can we substitute 2 here directly? Sorry? Yes, you can use the quotient rule to break apart. Or you can factor it, okay? And try to somehow cancel the like term, okay? Because here, when we plug in 2 to this denominator, it becomes 0, so we cannot substitute this here directly. So we need to do some algebra. And how can we do it here? Thank you. We should somehow factor it out, right? Factor it out, it means we need to somehow write x squared minus x minus 2 in terms of something, multiply something here, right? And the trick I gave you yesterday. And remember, just a reminder, ax plus a times x plus b. When we distribute this, it will be what is it? What is the last term? Okay, remember it? Now we do the reverse order. Okay, if we are given this guy, we ask ourselves which number are they, A and B in this case. Okay, and we see that here. Imagine we look at this. The numbers are this product, right? Or in other words, we are looking for the number A and number B such that A times B is equal to -2 and A plus B is equal to what? Yes, -1. Good job. Okay. So what is A and what is B? Good job. Or in the future, you can do it fast. If after some practice, you do it faster. Okay? There are many other ways, but this is one way. If you're not sure if this is correct or not, we can always double check it. Okay? Let us do it together. X minus 2 times x plus 1. When we distribute this, what do we have? Yes, x squared and let's go in this order. I get used to it. So then x times 1, it will be very good. And here, minus 2x, very good. And here, minus 2 times 1, right? Then we simplify it. It will be x squared minus x minus 2. So our computation was good. It's correct, right? Okay. Are we good? Then, now, since we know this, we can always write it as x approaches 2 of x minus 2 x plus 1 divided by x minus 2. Then, what should we do with this? Yes, they cancel out. It becomes, now it's easy, right? Then we can substitute this. It will be, good job. So the limit of this when x approaches 2 is equal to 3, but f at 2 is equal to 1. Then it violates the definition of the continuous function, right? Therefore, it is not continuous, right? So it is not continuous. Is it clear? Any question? People on Zoom, is it okay?
Yep.
Okay, good. So let us continue. The first graph is the graph of this function. As we can see, at 2 it is undefined. That's a hole here. It is discontinuous at this point, right? This is the graph of the second function. At 1, at 0, it is 1, it is this point. And x is different from 0, it follows these two paths. And this is the third guy. Same graph. And at 2, it is defined as 1. Okay? So, this types of discontinuous, we call it removable discontinuous, because at this point, it is removed. Okay? Removable, this point. At the second graph here, the limit, when x approaches 0, go to infinity. So it makes sense to say it is infinite discontinuity at this graph. Okay? Just some names. And here, the third case. So it is discontinuous at this point. It jumped down here, go back again and continue. So we call it a jump discontinuities. Okay? Just some names. Forget about this graph. Now, is it clear? The definition of these: continuous, removable, infinite discontinuous, and jump discontinuous. It will appear in the test 1, right? This piece of cake, just if you remember the definition, you can write it down quickly. Is there any question? Okay, good job. Now, let us consider this function. The function f of x is equal to this. It is called, let me remind the name of this, the greatest integer function. So it will return the value of this is like this. So the graded value, for example, it means if we consider 4.8, this case, this function, this operator will return the greatest integer that is smaller than this value. And what is it in this case? 4. Okay, just a definition. How about the greatest integer of 4.6? What is it? The same thing, right? Good job. 4. How about the greatest integer of 4? It's still 4, smaller or equal to this value. Okay, just a definition. So now, quickly, graded integers of 3.4. Good job. Greatest integer of pi. Yes. So, very good. Just a new name for this. And this is the graph of this function. Okay. When x is between 0 and 1, it will be this line. When x is larger than 3, for example, it will be this line. But at 3, it will be 3, right? This value. Therefore, it is a solid point right here. And here, 2.9, right? For example, x is 2.9, then this function return the value is 2. Therefore, the graph of this should be this line. At 2 will be this point. But at 3, it jumped here. Okay? This is another example of jump discontinuity. Okay? Are we good? Good. So then the next slides. If a function is continuous from the right at the number a, it means that the limit of the function here, when x approaches a plus, or from the right side of a, is equal to the value of the function at a, then we call it continuous from the right. Similarly, if the limit of f of x when x approaches negative a is equal to a, then we say it is continuous on the left. Okay? Here, look at the graph here. What is the limit of this function where f of x is the greatest integer function when x approaches 2 from the right? Yes, good job. It is 2, right? Great, Isaac, thank you. What is the value of this function at 2? It's satisfying the right-hand limit, continuous of the right-hand limit, right? So we say this function is continuous from the right. Okay. How about the limit of this function when x approaches 2 from the left? Yeah, be careful. It is just 1. Okay. It is different from f at 2. Okay. Therefore, it is not continuous from the left. So, you see it? Good. Then, another concept. Look at this interval from 1 to 2. We say that it is continuous in this interval if it is continuous at any point in this interval. Just a new concept. Okay? Very good. Good job. Then let us play with this example. Can you follow, or do you need to write it down or something? Are we good? Okay. Now, do this example. Show that the function f of x is equal to 1 minus square root of 1 minus x squared is continuous on the interval from -1 to 1. Do you know the name of this function? It invoked the radical sign. So we call it the rational function. Okay? This is the square root sign. What is the condition of the thing under the square root sign here? Someone said positive. Thank you, Madison. So the condition is that 1 minus x squared should be positive definition of radical function. Okay? What does it mean? Can we find the intervals of x that satisfy this condition? What should we do? We subtract both sides by -1 or whatever way. Can you say it again? If we add both sides by -1, what do we have? Then it will be okay. Then what should we do? Yeah, the negative sign is annoying. So we get rid of this by dividing it by -1 or multiply it by -1, right? The same thing. It means if x squared, the right hand side becomes 1. But what is the sign here? Yes, perfect. Right? Then square root of x, right? Or look at this. Imagine 0 is right here, -1 right here, 1 right here, right? So in order to solve this inequality, if we take square root, it would be absolute value of x, right? Okay. We take square root of both sides. The left-hand side will remember square root of something, then we take, it should be an absolute value right here. And then, what does it mean? Yes, x should be between the definition of absolute value is this. Absolute value of x is the distance from that point to the origin. The distance of this is smaller than 1. It means it should be larger than -1 and smaller than. Makes sense, right? Or if we write it slowly, or in that. This is another way to write this thing. Okay. In other words, we do some algebra, and we know that this guy is defined when x is larger or equal to larger than -1 and smaller than 1. I mean, or equal. So therefore, what? In other words, the domain of the function f of x is d is equal to this interval from -1 to 1. Okay. We haven't done anything yet. Just review how to find a domain of a radical function. Okay? Do it slowly. We got this. Now, they say that we need to show this is continuous in this interval. Okay? And this interval is the union of the point -1 and the interval from -1 to 1 and the point 1, right? Just notation, I break it into different things. This is open interval. So we do case study, case 1. When x belong to the interval from -1 to 1. Okay? What is the limit of this function when x approaches a? For a belong to this interval. We substitute this, right? We just rewrite the function f of x. Which limit law should we use here? Subtraction law, right? Very good. So it will be the limit of the constant. Subtract the limit of this when x approaches a. Okay? Then, what is the limit of a constant? Yes, it's a constant here and here. Since a is a number larger than -1 and smaller than 1, the law for a radical function, right? What is it? Limit of the radical law. And what is it? Here. Yes, 1 minus, when x approaches a, then 1 minus x squared will become 1 minus a squared, okay? Okay. Then what is f of a for any number between this interval? Right. It is exactly f of a. Therefore, it is continuous in this open interval. Try to go home and argue with the case when x is equal to -1 and x is equal to 1 here. And we'll continue tomorrow.